Hello, and thank you for joining us for this final talk in the I Heart Pluto Science Speaker Series. This series has centered around various interpretations of our theme, Worlds Revealed. In tonight's final installment, we return to our home planet, Earth, and look at it from a different perspective. My name is Amanda Bosch. I am a planetary scientist at Lowell Observatory. And also the Chief Operating Officer. This past Friday was the 92nd anniversary of the discovery of Pluto. And please excuse me for 1 second. I think I have sorry, I had some feedback there that I needed to correct. Sorry about that. So this past Friday was the 92nd anniversary of the discovery of Pluto, which we're celebrating at this I Heart Pluto Festival. You can find more information about the festival by visiting our website, iheartpluto.org. Previous science talks are also available to view at this website or on our YouTube channel. Before we get started, I'd like to thank Peppercorn Games in Flagstaff for sponsoring tonight's science talk. Our speaker tonight is Brent Minshew, who is the Cecil and Ida Green Assistant Professor in the Department of Earth, Atmospheric, and Planetary Sciences at MIT, where he leads the Remote Sensing and Glacier Dynamics group. Brent received his bachelor's and master's in aerospace engineering from the University of Texas at Austin in 2008 and 2010. He earned his PhD at Caltech in 2016 and was an NSF postdoctoral fellow at the British Antarctic Survey from 2016 to 2018. Brent's research interests focus on the flow, deformation, and fracture of glacier ice. He uses remote sensing observations and simple physical models to study the mechanics of rapid glacier flow. Before we get started tonight, I'd first like to let our viewers know that you can type your questions into the chat box and we'll pass them on to our speaker. Welcome, Brent, and we're looking forward to hearing about the coldest locations on Earth.
Okay, thanks, Amanda. And thanks everybody for coming, whether you're tuning in live or watching the recorded session of this. So I'm going to switch over and start sharing my slides right now. So my talk is entitled Lessons Learned from Observing Earth's Cryosphere from Satellites. So this is the kind of thing that I do. We really do a lot of work within my group, and I really enjoy looking at Earth's ice sheets, particularly Antarctica, as we're going to talk about today, using remote sensing observations. And sorry, I'm not sharing my screen. There we go. Now I'm sharing my slides. Everything looks good?
Looks good.
Shared? All right, very good. Yeah, so again, title of my talk, Lessons Learned from Observing Earth's Cryosphere from Satellites. So before I get started, I wanted to take a little bit of a trip to tell you a bit about my life and kind of how I came to be where I am now. So working as a scientist, working as a professor at MIT, studying Antarctica, sea level rise, this kind of thing. For me, it wasn't entirely a linear path. So I grew up in Texas, rural part of Texas. I grew up riding horses and raising pigs and things of this nature, never dreaming of being a scientist. Instead, whenever I graduated from high school, I decided to join the Marine Corps. I went off and served about 8 years or so on active duty in the Marine Corps and did a number of interesting things. So I spent a little bit of time serving on the helicopters that fly the president and the vice president around and this kind of thing. So you can see a picture down here of me with Al Gore when I was a little bit younger. This is back in 2001, around the inauguration of Bill Clinton as the new president. So I served 8 years in the Marine Corps, went on, as Amanda mentioned before, to the University of Texas after that. I got my undergrad and master's degree in aerospace engineering. I went on there and did some internships at NASA's Jet Propulsion Laboratory, where I discovered remote sensing and the kind of things that I do now. And that inspired me to go on and pursue a PhD, pursue a career as a scientist using remote sensing observations to study the ice sheets, to better understand how the ice sheets are evolving and changing, do a better job of projecting what we think sea level rise is going to be in the future. So as part of my current work, I spend a little bit of time in the field. There's just a fun photo up on the right-hand side of goofing around, swimming with icebergs and this kind of thing. And of course, I try to maintain a general sort of stated work-life balance. So raise my daughter, build Legos, play around with her, this kind of thing. So no single path to a career in science, if anybody out there is watching and is interested in growing up to become a scientist. So what I do now, I would describe myself as a geophysicist who studies glacier dynamics. And what that means is that I'm very interested in the physics of glacier flow, and more specifically using classical mechanics to understand the flow of glaciers. So glacier ice, just like any ice as we experience it, is a solid, but over long enough timescales, so timescales over longer than about a week or so, it flows as a viscous fluid. And I really love this particular image of a glacier called Elephant's Foot Glacier in Greenland. It's a beautiful example of what's called a Piedmont glacier. So you see the glacier ice is coming out, it's flowing and it's spilling out, and it's spreading across the ground at lower elevation, much like honey or syrup would spread across a plate. So this is a beautiful example in a picture of sort of the viscous nature of glacier ice. And this is one of the things that we study using observations that we collect from satellites, physical models, this kind of thing, to infer properties of the ice, the viscosity of the ice, the coupling between the ice and the bed, and so forth. The big overarching questions that we try to get at, though, is understanding how do glaciers and ice sheets respond to climate change, and how do glaciers and ice sheets shape the solid Earth? So I got really interested in studying glaciers fairly early on in my graduate work. And a big part of my interest in studying glaciers was that they're just an integral component of the Earth system. So glaciers help to shape landscapes, such as the iconic Yosemite Valley that's shown here and the photograph in the background. Glaciers also influence and are influenced by the climate and the Earth's oceans. Glaciers support complex ecosystems from microfauna to macrofauna. And of course, we have to throw in gratuitous pictures of penguins in the background as we're going to be talking about Antarctica. And then glaciers are finally the world's largest store of fresh water, in particular in the Antarctic ice sheet. And so storage of fresh water is one of the primary things that we think about when we're thinking about glaciers and ice sheets and how they're evolving in time. That is, specifically, we're concerned with how much they may contribute to sea level rise and how fast they may contribute to sea level rise. So at the moment, whenever we're projecting out sea level rise and trying to understand what's going on, at least within a human lifetime, our projections have a relatively large degree of uncertainty. That is to say that our current projections, we estimate that mean sea levels may rise by somewhere between 20 centimeters and 2 meters or so by the end of the century. And this meter scale uncertainty creates this major obstacle to planning and mitigation. So you can get some sense of that in the maps that were shown down here. So this is our home at MIT. It shows the location of the main building there in the picture within the little map view here. So what we're showing on the left is what this area of Boston and the campus of MIT is going to look like under relatively low end projections, so about 20 centimeters or so sea level rise by the end of the century. This area looks more or less like what it does now. We can expect to see increased flooding events and so forth from storm surges, king tides, things of this nature. But we have decent solutions to this in that we can build coastal barriers and whatnot to deal with this nuisance level of flooding. But in the high-end projections that we're showing on the right-hand side, increase in sea level rise of about 2 meters or so by the end of the century. What we're showing is picking up is a lot of these blue areas. And these blue areas are areas that are likely to be below sea level at mean sea level itself, which is pretty much the entire campus of MIT and a number of the other surrounding areas. And so this realm of possibility, this range of possibilities that we get from our current models is something that's really, really hard to deal with, because the flooding solution, like the one on the right, essentially entails having to move large portions of the city. And so between the low-end projections and the high-end projections, we're talking about trillions of dollars of difference in infrastructure and completely different plans for dealing with and managing the risks to sea level rise. And so one of the things that we work on within the group and using remote sensing observations to study the ice sheets is trying to get a better understanding of what these uncertainties are. Ideally, we would like to shrink the uncertainties But at the very least, we would like to contribute to doing a better job of quantifying the uncertainties so we have a better idea of which one of these outcomes, the low end projections or the high end projections, is more likely in the future. And a lot of this uncertainty and the way we feel like we can contribute to this is that a lot of this uncertainty is really driven by a poor understanding of ice sheet dynamics and the interactions between ice sheets and the ocean. So this kind of thing is what gets people fairly worked up. So you can see a number of kind of scary looking headlines that come out all the time. People talk about ice apocalypse, doomsday glacier, things to this nature. And all of this is kind of related to this possibility of really rapid sea level rise that we discussed in the previous slide. So how do we know how ice sheets are changing and how do we know they're losing mass? Well, one of the methods that we can use via remote sensing observations is to simply weigh the ice sheets. And we do this by using the orbits of satellites in order to provide insight into the changes in mass. And so one of the primary instruments that we have available to us to do this kind of thing is an instrument called GRACE, and eventually and its successor, which is known as GRACE Follow-On. This stands for Gravity Recovery and Climate Experiment. And so what this is a pair of satellites that's flown by NASA. And what happens is these satellites fly over and they're very precisely measuring the distance between these two satellites. So as they fly over in some sort of mass anomaly on the ground, the leading satellite will accelerate, open the distance between these two satellites. As it passes over, the distance will close. As it passes over again, the distance will open back up and so forth. So there's this nice accordion effect that takes place between these two satellites that allows us to measure very precisely changes in mass on the ground. So we're able to effectively weigh the ice sheets using this pair of satellites as they orbit over the Earth. And when we look at the data and we start to get a sense of what's going on in Antarctica and what these data are telling us, what we see is a little bit concerning. So these are the observations that we're showing and the data that we see. And so on the left-hand side, what you're seeing is a plot of the change in mass in Antarctica, the total change in mass in Antarctica over the past roughly 20 years or so. Now, the units that are given here on the y-axis are given in gigatons, which is not the most intuitive unit unless you think about this kind of thing all the time. But a gigaton of ice is basically an ice cube that is 1 kilometer on each side. So the numbers that we get out of this and total amount of mass that's being lost from Antarctica is somewhere around 150 gigatons or so per year. If you want to take that and put it into context, at least within Arizona, for example, where the Lowell Observatory is located, if you took that number and you stretched it out, that total net mass loss, and you distribute it evenly across the state of Arizona, what you would end up with is a sheet of ice that's about 0.5 meter or so per year of ice that's covering all of Antarctica. So that's the net mass loss that is occurring on average from Antarctica every single year. Over the past 20 years or so, what we end up losing is somewhere around 3,000 or so gigatons per year of net mass loss from Antarctica. That accounts for, that's about an 8 millimeter or so sea level equivalent, which accounts for somewhere around about 1/100th of 1% of the total mass in Antarctica. So though we're losing a lot and contributing somewhat to sea level rise, there's still quite a bit of mass left to lose. And so the mass losses are not constant or not evenly distributed in space. They're localized in a few areas. In particular, I can't see my pointer actually, but in particular, you'll notice an area kind of on the left-hand side here, where you see this relatively dark red area. This indicates the most significant sources of mass loss in Antarctica over the past 20 years or so. And this area, which is known as the Amundsen Sea sector, is an area that we're particularly concerned about in terms of the stability of West Antarctica and the potential for rapid sea level rise, as we'll talk about in a bit. But all these pieces, all this data kind of comes from this pair of satellites that we have flying over that gives us the ability to weigh the ice sheet from space. So what other tools do we have at our disposal? Since this is mostly an astronomy-focused session, I wanted to come back around and talk about some of the tools of astronomy effectively that we use to turn around and look at the Earth system itself. So we use lots and lots of different satellites that most of them take advantage of various parts of the electromagnetic spectrum. So we have a number of satellites that are flying around in orbit that take pictures for us in the optical spectrum. So we have pictures up here on the top right-hand side, which are photographs of a collapse of an ice shelf known as the Larsen B ice shelf in Antarctica, which collapsed in 2002. It was a large ice shelf. An ice shelf is a floating extension of the ice sheet. There's a large ice shelf, an area about the size of Rhode Island or so, and an ice shelf that's a couple hundred meters thick or so, that has been there, that was there for at least since the last glacial maximum throughout the Holocene, and is something that collapsed and shattered into thousands of pieces that you see in this photograph over a time scale of a couple of weeks. So we have these kinds of observations of these rapid changes that are taking place within the ice sheet that we use to our advantage to try to understand the physics that that govern the ice sheet, and to develop models that allow us to project into the future. In addition, within the optical spectrum, we now have new instruments that are flying around that are laser altimeters. So they're firing green lasers down, and they're making very precise measurements of the surface elevation of the ice sheet and changes in surface elevation over the ice sheet itself. And this gives us a great data set to do a better job of understanding the mass balance of the ice sheet, how quickly it's losing mass, how it's changing over time, and so forth. We can move on to the longer wavelengths, and we have instruments aboard satellites that give us a view into the infrared, both the near infrared as well as the thermal infrared. So there's a really nice image here on the right-hand side that's taken from a thermal infrared camera that's flying aboard NASA's Landsat 8 satellite. And this is of a large iceberg that is broken off of another ice shelf in Antarctica known as the Larsen C ice shelf. This is a wintertime image, and we're able to see for the first time in this image the breakoff of this giant iceberg that then floated off into the Atlantic and has recently broke up into much smaller pieces. But the thermal signature gives us the ability to see areas of relatively open water, areas that have relatively thick sea ice and so forth, and it is indicated by the warmer temperatures in the ocean water, as well as the areas of relatively thick sea ice that are indicated by the colder areas. And then the coldest areas, these are the glacier ice itself. So portions of the ice shelf and the piece of the iceberg that is broken off. As we move further out into the electromagnetic spectrum, into even lower frequencies, what we get into is a range of microwaves, and in particular, radar observations. And this is the kind of thing within my group that we do quite a bit of. We use radar observations from satellites, such as we're showing on the GIF here on the right-hand side of an iceberg that's calving off of an area called the Brunt Ice Shelf, which we'll revisit in a little bit. These observations that we use from radar, we get a lot of mileage out of them, both in terms of the images, like the amplitude image that you see here on the right-hand side, and we use these observations in order to estimate the velocity fields, the deformation rates, things of this nature of the ice. And we'll talk a little bit in just a second about how this kind of thing works. So before we get there, I want to tell you a broader story about what's happening in Antarctica and the contribution of Antarctica to sea level rise. And in Antarctica, since it's relatively cold all the time, the story of its contribution to sea level rise is really all about the dynamical component of mass loss. So what we're showing here on the left-hand side is an image that is collected from thousands and thousands of observations from satellites and measurements of the surface velocity that we get from these various satellite observations. And so one of the things that you'll notice, the scale bar here in this area, so yellow to black, indicating slower to faster velocities, with the fastest velocities that we're showing here around 3 kilometers or so per year. One of the things that you'll notice in this image is that the relatively fast flowing bits are all concentrated into these streaming type features. So these are the fast flowing glaciers and ice streams that we're particularly interested in studying within my group and research that we do. And then the areas that are relatively large and have relatively fast flowing bits, these are the floating ice shelves. They're the floating extensions of the ice sheet itself. And so what's happening in Antarctica really is that basically what happens is that every single snowflake that falls in Antarctica is compressed into glacier ice, and it flows through one of these fast flowing glaciers ice streams and eventually ends up on one of these floating ice shelves, where it's lost to the ocean either by melting off the base of the ice shelf or by calving off the front of the ice shelf. Now in Antarctica, for most of the changes that we observe at the moment, really the story is primarily about the melt that's taking place from the ocean off of the bottom of these floating ice shelf bits. So on the right-hand side here, what I've done is taken the same image on the left, but now I've grayed out these areas of the floating ice shelves just to make it clear where those are. And then we've laid underneath that a plot of the observed ocean temperatures. So these are the ocean temperatures that have been observed from floats. They've been interpolated in space, and they're averaged over the depths that are relevant for these floating ice shelves. And so what you'll notice around most of Antarctica is that we have relatively cool water that has gotten up onto the continental shelf, which is shown by this heavy black line. So relatively cool water that's gotten up onto the continental shelf, as indicated by the blue colors here. And this cool water is coming into contact with the floating ice shelves. But there are a few areas, such as in the Bellingshausen Sea sector, which I can't see my pointer anymore, the Bellingshausen Sea sector and the Amundsen Sea sector, which is the areas that have the relatively warm water that's gotten up onto the continental shelf and is coming into contact with the floating ice shelves themselves. And these are the areas where a number of interesting changes are starting to take place. So in general, where we see these warm water coming up onto the continental shelf and coming into contact with the floating ice shelves, what we're observing is the ice shelves themselves are thinning. So that's what we're plotting now here in the purple to green observations. So these are measurements that are taken with laser altimeters that are aboard a satellite known as ICESat. So these observations are sort of averaged over the past 15 years or so and show the rate of thinning of these ice shelves. So the deeper the purple, the faster the rate of thinning. So you'll notice in all these areas that have relatively warm ocean water is indicated in the red colors that are coming into contact with the ice shelves. And those ice shelves are showing relatively purple or deeper purple colors, indicating relatively fast rates of thinning of the ice shelf. In some places, the thinning is up to several meters per year, which is a considerable fraction of the thickness of the ice shelves. These ice shelves in these areas are only a couple hundred meters or so thick to begin with, and they're losing the net loss of several meters or so per year of thinning on these ice shelves. So in general,
just jump in here for a second. We have a question just about the implications of having this melt of these glaciers. So are the glacial sheets freshwater? And then if they do melt, does that have any sort of effect on the salinity of the surrounding sea?
Yeah, definitely. Yeah, that's a really good question. Yeah, so glacier ice is formed from compacted snow, so it's always fresh. And so the melting that we get from the warm ocean water certainly has a freshening effect on the surrounding ocean. In fact, this is one of the prevailing models that people have put forward to argue for the fact that to explain why the sea ice pack around Antarctica appears to be growing, despite the fact that the climate is warming. So the argument goes this freshening effect, particularly the freshening effect of the ocean surface, makes it such that the water is easier to freeze, easier to form sea ice around this area. So,
because salt water freezes at a lower temperature. Is that okay?
Yep, and there's an additional bit to this as well. So there's a fascinating mechanism related to the buoyancy of the fresh water as well. So you have an ice shelf that's much deeper as you move inland and so forth, and it starts to thin out. And so this warm ocean water, whenever it comes in, the warm ocean water tends to be relatively deep because it's very salty. And it comes in and it contacts the ice at its deepest point, which is also where the ice is easiest to melt because the melting temperature of ice is depressed under pressure from the weight of the ice above it, right? And so this warm ocean water comes in and it contacts the ice and it melts the ice. So that creates fresh water. Fresh water is buoyant in the presence of the salt water and so forth. So it creates this buoyant plume that goes up underneath the ice shelf. And that creates this almost like this self-sustaining pumping mechanism. So as you create this buoyant fresh water, it starts to draw up, it pulls more ocean water toward it and so forth. And so there's a sort of a sustainment, almost a quasi-sustainment mechanism for continuing to pull more warm, salty ocean water toward the ice shelves and enhance the rate of melting and so forth. So,
do you know if it affects the sea life having adding in the fresh water? Because I remember seeing something recently about just the sea life underneath or on the seafloor near there, and I'm just wondering if that has any effect.
Yeah, I mean, presumably it does. We don't have great observations of that, and I'm not sure that the salinity changes dramatically enough to have immediate impact on the ocean life under there. But one of the things that it can do is that I'll step back a little bit. So Antarctica is a fascinating place. It is the world's largest desert on the surface, and it's basically the world's largest wetland underneath the ice sheet, right? So you have all these active rivers and lakes and so forth that are flowing around there. And so you have this discharge coming out of Antarctica from the grounded ice itself, which is also fresh, and it's carrying a lot of minerals, iron, things like this that have been churned up from the glacier, because glaciers are amazing agents of erosion, right? So as they're flowing along, they're chewing up the ground underneath, they're carrying all these minerals to them and so forth. And so the fresh water that's flowing out from underneath the glaciers is carrying a lot of this absorbed in it. And then in addition to that, you have these freshwater plumes that are coming in due to the melting that's caused by the ocean itself. And so that carries this very nutrient-rich water out into what amounts to open ocean, these areas that are called polynyas, these patches of open ocean that are surrounded by sea ice, and they're open because they have these big plumes of heat that's coming up and so forth. And these are some of the most biologically productive waters on Earth. So you have this very mineral rich, very iron rich water that's coming out of there. So we have these big plankton blooms, you have whales, you have all kinds of other things showing up to feed within these giant polynyas. And so this discharge that comes out from the Antarctic ice sheet, as well as a number of other glaciers, is actually critical to maintaining these very complex ecosystems that tend to exist within the polar regions. And it's all kind of, again, sort of driven by this, in part or in large part, by this buoyancy of fresh water within this saltwater environment. So there's a nice feedback between the physics and the biology and so forth of this area.
Wow, thank you. That's fascinating.
Yeah, it's a great question. Thanks for asking. And definitely feel free to jump in and interrupt me anytime with questions. So last little bit on this particular story then is thinking about the response of the glaciers then to this thinning of the ice shelf. All right, so you have this warm ocean water that's coming in, and it's thinning the ice shelves. And in general, where we see the ice shelves thinning, we see the glaciers and ice streams that are feeding these ice shelves starting to speed up. And in Antarctica, this is entirely the sea level rise contribution, right? The change in the rate of flow, the rate of transport of ice from the grounded ice into the ocean that gives us our sea level rise signal in Antarctica. And so that's basically what we're showing here on the right-hand side. So this is the change in observed flow speed, the flow speed that's been observed by satellites over roughly the past 20 years or so. Positive values indicating a net speed up. And so it's all along these areas in the Amundsen Sea sector that we showed before, and that we saw within the GRACE images that showed the overall loss of mass. All of this corresponds and is driven by this increase in the rate of transport of ice, that is increase in the flow speed of the glaciers that are feeding into this area. So this connection, again, sort of closing the loop between the warm ocean water coming up, thinning the ice shelves, causing the glaciers to speed up, and thus we get a net mass loss from Antarctica and sea level rise. The reason that this is happening is that ice shelves provide a very important resistive stress to the flow of the glaciers. So on the left-hand side here, we have this very simple cartoon of a glacier that's flowing down. So from the grounded ice that's flowing down and starting to float onto the ocean. The boundary between the grounded ice and the ocean is something that we refer to as the grounding line. The ice shelf is downstream, the ice sheet is upstream, and so forth. So whenever the ice is flowing down and it gets onto the ice shelf, and whenever that ice shelf is either confined on its side or it's pinned at discrete points underneath, it provides this resistive, or what we call buttressing stresses, that tends to hold the ice a little bit onto the ice sheet, keeps it onto the land. But whenever we start to thin the ice shelf, bringing in this warm ocean water, starting to thin the ice shelf, what we do is we reduce these resistive stresses, we reduce the buttressing stresses of the ice shelf, and it allows the ice to flow faster toward the ocean. And this is the thing that results in sea level rise. And that is this dynamic response basically makes these ice shelves this critical vulnerability of the ice sheet to climate change. And this is something that we're particularly concerned about because the ice shelves in general are the furthest north extent of the ice shelf. They exist at the lowest altitude. And so they are themselves the most vulnerable to climate change. They're going to start to warm up first. And then they allow for this significant and dynamic response of the overall ice sheet, loss of mass, and sea level rise, and so forth. And this is especially true in areas that are known as marine ice sheets, like West Antarctica. Noticing a few questions come in.
Yeah, if you don't mind, I'll just jump in here. Sophia asks, She says, I can see why it's studied extensively from space because it sounds like everything is shifting there. Has it been safe enough to send research teams there for on the ground confirmation and observation?
Absolutely. Yeah. So teams go down to Antarctica all the time. So the United States, United Kingdom, Germany, Korea, China, Russia, all these countries operate research stations down in Antarctica. So scientists are pretty much down there all the time. They're taking all manner of measurements, not least of which observations that teach us about the state of the ice sheet itself. So researchers definitely go down there. They will take observations. So for this kind of work, for example, they'll take observations of the flow speed of the glaciers using GPS observations. They'll go down there with a whole host of other instruments that will measure the thickness of the ice sheet. They will drill into these ice shelves and measure the ocean properties underneath the ice shelves. So temperature, salinity, and so forth of the ocean, all kinds of things, a whole host of observations. But one of the reasons why we tend to use satellites a lot in this particular area, though, is that Antarctica is really big, and most of it is quite remote. So I didn't mention it earlier, but we had one of the plots before where we have the continental United States plotted over top of Antarctica, and Antarctica is, roughly sort of twice the size of the lower 48 in the US. And so even though we do have teams down there, they're very sparse. And the areas that they can reach are small compared to the total size of Antarctica itself. And so we get a lot of mileage out of satellite observations and this ability to cover the entire continent for the most part in observations, measure what's happening more or less in real time, and then often go in and do detailed studies with teams that are there on the ice itself and calibration and validation and so forth of the satellite observations that we make on the ice.
Yep, great. We have another question this one from Stephen. Is there a long enough baseline of satellite observations of ice flow in Antarctica to be able to tell if the flow rate has been increasing, and has that been correlated with atmospheric temperatures?
Yeah, so we have about 20 years or so of decent velocity measurements in large portions of Antarctica. And so we can definitely see increases in velocity in a number of areas. So in Antarctica, it's not necessarily correlated in a lot of areas with increases in atmospheric temperatures. Again, it's correlated primarily with changes in the local temperature, the temperature of the seawater that's local to Antarctica. So it's really the ocean that's primarily driving the changes that we see in Antarctica at the moment. Now, if you get out onto places like the Antarctic Peninsula and so forth, so the northern parts of Antarctica, there are definitely relationships between the flow velocities that we see, the general health, if you will, of the ice shelves in that area, and atmospheric temperatures, atmospheric conditions, and things of this nature. But around the majority of Antarctica, the changes that we're observing are driven primarily by the ocean. So changes in the westerly winds around Antarctica that are pumping this warm, deep ocean water toward the continental shelf, toward the ice sheet itself, melting, thinning these ice shelves, and allowing the glaciers to speed up. Mm-hmm. Now in Greenland, Greenland's a different story, and pretty much the rest of the glaciers in the rest of the world are a different story. We definitely see a relationship between warming atmospheric temperatures and the flow speed of glaciers and so forth. So as the temperatures warm up, sort of to a crude approximation in some areas, we do see glaciers that are starting to speed up, calving rates are increasing, and so forth.
Do the Greenland glaciers have a similar ice shelf over water, or what? So it's all over land?
Yeah, so there really isn't much to speak of in terms of ice shelves in Greenland. There are a few left, but they are relatively rare, and they're probably not going to be with us for all that much longer. Mm-hmm. Greenland is just much warmer, and so it is harder for glaciers in Greenland to maintain significant ice shelf for any real length of time. So most of the glaciers that we see in Greenland are what we refer to as marine terminating glaciers. So these are just glaciers that are flowing into the ocean, and then they're calving off icebergs directly into the ocean with little to no flotation before the calving event itself.
Okay, thank you.
Mm-hmm. Okay, so moving on. So thinking about this idea, this notion of a marine ice sheet, like the one we see in West Antarctica. So a marine ice sheet is an ice sheet that is primarily resting on the seafloor. And in general, the weight of the ice sheet depresses the ocean crust, and so it causes the bed in general to deepen as it moves inland. The only marine ice sheet that we have right now is in West Antarctica, and we're particularly concerned about this, and we focus quite a bit of our research on understanding what's going on in West Antarctica because we believe that marine ice sheets are an unstable configuration simply due to the fact that ice floats. So because of this, you get this buoyancy-driven feedback that can happen, that as we start to thin glaciers, more of them start to float. This decreases the resistive stresses that are provided by the bed, allows the glacier to flow a little bit faster. It starts to thin more, starts to retreat more, and so forth. So there's this instability we refer to as the marine ice sheet instability that is simply this buoyancy-driven feedback that acts similar to sort of like peeling a rug off of a floor when you start to pick up a piece on the side. And so West Antarctica, being the only marine ice sheet that we have, is a thing that we tend to concentrate on in thinking about rapid sea level rise, massive uncertainties in sea level rise, and so forth. In fact, most of the uncertainties that we talked about before, this difference between 20 centimeters of sea level rise and 2 meters of sea level rise by the end of the century, primarily comes from West Antarctica. And so what we're showing here is kind of these bits and these different cutaways of what's happening within West Antarctica. And so this area that we're showing here on the right-hand side, this is a map of the bathymetry. So this is the height of the bed beneath the ice sheet itself. And so if we were to take and just lift the ice sheet off of the bed, keeping sea level rise or sea levels where they are right now, this is more or less what the topographic map of this particular area would look like. So East Antarctica, you can see, is basically a continent. Well, it is a continent. And so it's an ice sheet that's sitting on a continent. But West Antarctica, this area that's circled within this black ellipse here, is essentially an archipelago that's filled in with an ice sheet, right? And so you can see from the color map over here in these relatively deep blue colors that the West Antarctic ice sheet is sitting on the seafloor that's about 2 kilometers or so below sea level. And it's these areas that we've pointed out before in the data, both the GRACE data in the top left-hand side, as well as the change in velocity data that we're showing down here in the bottom on the left-hand side. It's this area, these relatively deep bits where the ice is sitting on the seafloor that are speeding up, that are losing mass, and so forth. And again, due to this buoyancy-driven feedback, we have the potential for rapid and potentially catastrophic rates of sea level rise that come from this particular area. So how do we know that?
Just jump in here because we have a question from James asking about this phenomenon. So what would happen if the ice loss is great enough? Would the seafloor rebound? If you lost enough ice?
Oh yeah, definitely. So the crust is depressed due to the weight of the ice sheet itself, and so as we start to lose mass from the ice sheet, then the solid Earth will rebound eventually. So the rate of rebound of the solid Earth, there's a component of it that is instantaneous. This is the elastic response of the solid Earth and so forth. And then there's a component of it that takes place over relatively long time scales. And so one of the things that people have been looking at, like in active area research, is thinking about what this rate of rebound of the solid Earth would be and whether or not it would be enough to counteract this particular instability, that is to slow the rates of sea level rise that we would expect to see from this area. And the answer appears to be right now kind of probably not. And the reason for that is that the viscosity of the mantle of the Earth is relatively high. Now in West Antarctica, it's lower than it is in most other areas because West Antarctica happens to be sitting on a hot spot within Earth's mantle. And so the viscosity of the mantle is low by sort of Earth mantle standards. But nonetheless, the time scale over which we would expect sort of the viscous rebound of the solid Earth to take place is sufficiently long that it won't have a major influence, or is unlikely to have a major influence on mass loss from West Antarctica. So we can still basically lose a significant amount of mass from the West Antarctic ice sheet over time scales that are much shorter than the response of the solid Earth to those losses. So eventually the solid Earth will rebound, but probably not enough to necessarily impact too much the rate of sea level rise that we might get from this area.
So this is a portion of the 20 centimeters to 2 meter issue, but not a large portion.
Yeah, pretty small. The 20 centimeters to 2 meter issue is really relates to this instability, as well as the potential for kind of structural collapse of the ice. So if we lose ice fast enough, basically we end up with these really tall cliffs of ice that can break off and waste away mass at a relatively rapid rate. We've never seen anything like this happen. And so there's a lot of uncertainties within the models themselves and the parameters that we use to drive these models. And this is the primary source of this sort of 20 centimeter to 2 meter uncertainty that we see in projections of sea level rise.
Thank you.
It's really pretty much all in West Antarctica.
Mm-hmm.
So getting back to observational methods and thinking about the tools of astronomy and so forth. So we can ask the question of kind of how do we measure this kind of thing? Like how do we know what the bathymetry is beneath Antarctica? How do we know the level of the seafloor and this kind of thing? And the short answer is that in general, we can use seismics, but primarily what we use is relatively low frequency radar. So we have a number of aircraft that are equipped with radars that have, transmit and sufficiently low frequencies. They have wavelengths of a few meters or so, and they're able to penetrate all the way to the bed of the ice. And so down here on the bottom left-hand side, we're showing an example of one of these radar echograms where you can really see this very distinct horizon lower in this radar echogram. That is the bed of the ice. So that is the base of the ice that tends to be a relatively strong reflector of the radar energy, because in general it's wet, right? And so the radar waves are transmitting through the ice, and it's getting down to this bed that's relatively wet. There's a significant difference between the electromagnetic properties of ice and the electromagnetic properties of water and so forth. And so it makes this really great reflector, bounces the energy back. And so people go in and they fly thousands of kilometers of flight lines of these types of observations. They go in and they click, in general, more or less by hand, and they pick out where the bed is in this bit. And then they stitch them all together, interpolate them in space, and we get these maps of topography like we see on the right-hand side. So getting back to the kind of the bread and butter pieces, the stuff that we've been talking about and thinking about how do we measure glacier velocities, and this gets at a little bit one of the questions that was asked earlier, which is really good. And thinking about how we measure glacier velocities, we can use field methods. People go out into the field, they use surveying techniques, they use GPS instruments. There's a picture down here that I took in one of our field campaigns of setting up GPS instruments on one of the ice. And the ice in this particular area happens to be in Iceland. GPS observations are really fantastic. They're good for making detailed measurements at a point or any particular or small area, and they provide really high time resolution. We can take observations of the position of the GPS instrument roughly every second or so, right? But the key sort of takeaway of this and kind of the key downside of this kind of thing is that they only give us these observations really at a single point. And so we start to fill in our observations and fill in our understanding of what's going on in these areas and making maps like we see on the right-hand side by using remote sensing methods. That is optical observations as well as radar observations. And these are things that are really good for covering relatively large areas, sort of like hundreds of square kilometers. We have variable spatial resolution for these various types of instruments, but in general, they range from about 10 meters up to a kilometer or so in spatial resolution. And they give in general, decently good time resolution. Right? So we have enough satellites that are flying around now that in general, we're able to take an observation of any area within Antarctica every sort of week or so. We take these observations that are collected from more or less the same point in space, but at different points in time, and we use them then to measure the surface velocities on the ice. And one common technique that we use to do that is by tracking the features that we can see on the surface using radar or the optical data. So just focusing on radar and the kind of ways that we measure it and go through these general properties of radar, right? So originally radar was an acronym. This is radio distance and ranging, right? So similar applications to what we see like down here on the bottom right-hand side, used at airports all the time, where you ping some signal from some fixed location and you listen for the echo of that signal to come back from an aircraft or whatever. So it didn't take people very long though to figure out that they could take the radar instrument, they could put it on one of these aircraft, They can send the signal down and listen for the echo of that signal as it comes back from the Earth, and they can learn a lot about what's going on the Earth. And so this is the kind of thing that we do now. So now radar is a much sort of broader term. It's often used to describe remote sensing methods that utilize microwave radio frequencies, and these exist in kind of the 300 gigahertz to sort of down to 100 megahertz range or so in frequency of electromagnetic radiation. So radar can be used in both passive mode, which simply means that we listen to the thermal noise effectively from the Earth and surrounding areas. That we just observe, or we just record the ambient EM radiation that's coming back. This is given to us by Planck's law and so forth for materials of a given temperature. Right, something that astronomers use and get a lot of mileage out of quite a bit. Now around Earth, where we typically use, and for the kind of work that we do, is an active radar system. So this is a little bit similar to what's going on down here on the bottom right-hand side. So we're transmitting some known signal down toward the Earth, and we're listening and recording that echo as it comes back to us. In general, we do this kind of thing, and we process it through this method that's known as synthetic aperture radar. And synthetic aperture is simply a method of processing the radar observations that takes advantage of the Doppler shift in the radar itself. And so what's happening really, and we're going to run this movie forward to give you an illustration of what's happening in synthetic aperture radar. Basically, what we have is a satellite flying along on the top left-hand side, and it's transmitting radar signals. Every one of these pulses that's going out is a radar signal that's being transmitted. And we're focusing really on this green target that's coming in down here. And you'll notice that as this thing transmits, it's illuminating this finite sized patch, this ellipse on the ground, right? And so whenever this ellipse is moving along, this radar footprint is moving along, and the target just first starts to enter it, we pick up a Doppler shift due to the fact that the platform and the radar itself is moving toward this particular target. And then we pick up a Doppler shift again as the target starts to move into the back end of this radar footprint. And we use this Doppler shift, right, this change in the frequency due to the motion of the radar itself, to start to focus our image. And so we can take lots and lots of pulses of this particular radar, and we can start to hone it in, and we can start to focus it. And as you can see in the top right-hand side of this particular movie, the image starts to get sharper and sharper and sharper over time as we collect more and more pulses, and we start to process these things together. So this is forming effectively a synthetic aperture. That is to say that our aperture, our antenna, basically it effectively starts to span the length of the flight line of our satellite, of our aircraft, or whatever it is. So it makes it really long and improves our resolution overall. I notice there's some questions coming in. Do we want to?
I'm going to hold until a little bit later for those, because they're not about this particular topic. So we'll get back to those.
Sounds good. Okay, so if you didn't necessarily catch all that, basically what you can think of as radar is, you can think of it as just a scanner for Earth's surface, okay? So we're flying over a satellite or radar, it flies over, and it's sending and it's receiving microwave pulses. The received pulses are going to be processed into an image that looks more or less like a black and white photo, right? Because it's the same basic idea. We're just using wavelengths that are longer than what we would for optical imagery. But nonetheless, same idea. So just as an example, on the right-hand side, this is a radar image that's collected from a satellite of one of my favorite ice streams in Antarctica, known as Rutherford Ice Stream. And so what you can notice in this particular image, on the left-hand side, you see all these sort of bright patches and bright features and so forth. This is a mountain range that exists on this side of the ice stream. You start to see these bright patches because you have all these facets of the mountain range and so forth that are really good at reflecting the energy back to the radar system itself. And then you can see, if you notice, so the color map on the backhand side, this is the velocity field of the ice stream itself, with red colors indicating faster flow, blue colors indicating slower flow. And within the radar amplitude image, this black and white image itself, you see these strips on either side where the velocity field is changing that are relatively bright. So these are surface crevasses that are formed due to the fact that the ice is deforming relatively rapidly in this area, opening up these big surface crevasses. And these show up very nicely in radar images because they're this nice randomly rough feature that radar really likes to bounce off of and come back to the satellites and so forth. And so these brighter areas indicate higher power return to the instrument itself. So there's a lot of information contained in these radar images that we can get. And what we ended up doing in order to understand the velocity fields of the glaciers, deformation rates of the glaciers, things of this nature, is we use a series of these images that are collected from the same location in space, but at different times in order to calculate the flow velocity of the glaciers and the ice streams. And we do this, one of the primary ways that we do this is by simply taking these images and tracking the motion of individual features that we can see in this image. So basically we'll take this image, and this particular area will be collected at one point in time. We'll take another image that's collected, again, from the same location in space, but at a different time, and we'll compare these two images. So effectively what we'll do is we'll go in and we'll cut out a patch out of one of these images. We'll slide it over. We'll calculate what's called the cross correlation, which just simply means that we're just multiplying a bunch of things together and adding them all up, and then looking what the outcome of that is. We slide this window over, we calculate, we add it all up, so forth, slide it over, multiply, add things up, and so on and so forth. And so we end up with essentially a map of these various correlation surfaces, and the peak of that correlation surface tells us about the displacement of this particular point in the time between these two observations, and then the curvature of the surface gives us an estimate of the error of that observation. And we repeat these things thousands and thousands of times, and what we end up with is a map of the displacement of these different points in the image in the time between the acquisitions of this radar signal. So this is just an example for this particular radar observation where we're measuring the displacement between images that were collected one day apart and along the radar line of sight. A radar is an oblique looking instrument, so its line of sight comes down to the surface at roughly a 45-degree angle, somewhere around in there. And so what we're able to measure in this particular instance, and what we're showing here, is both the horizontal and the vertical motion of the ice as it's moving through, simply by tracking these various features that some of them you can just see by eye within these images. So we do this kind of thing, and we repeat this for thousands and thousands of pairs of images and so forth, and we start to stitch these things together, and we combine them in, and that's how we get the maps like we were seeing here before. So these observations that are collected in this particular case from about 20 years or so of satellite observations, all stitched together to make this nice coherent map of the flow in Antarctica. Again, with the continental United States plotted there, so you can see this general sense of kind of the spatial coverage that we get from these remote sensing observations. And if we had more time, we would zoom in and you could see the exquisite detail that we're actually capable of capturing these things in. So in general, the surface velocity fields that we're getting here, we're going to get these in spatial resolutions of kind of, nowadays we can get down to 100 meters or so spatial resolution. The changes in that is velocity is resolved very well for us every sort of 100 meters or so step across Antarctica. Older versions, like the one we're showing here, resolved to kind of the 500 to 800 meter range, but that's still a pretty considerable accomplishment given the size of Antarctica and the kind of things that we're measuring. And we get precisions on these kinds of things down to just a few percent of the total flow speed of the glacier. So we can get very accurate measurements. The raw measurements themselves will give us accuracies and displacement of order centimeters. Once we stitch all these things together and make these big maps, we have errors of order about 10 meters or so per year, which is quite an accomplishment. So those are just the static looks where we take these observations and we make these big maps of Antarctica and so forth. And one of the things that we've been able to do in the past few years as we've gotten more and more observations is we're actually able to take these various measurements and we're able to put them together into a time series, and we're able to look at how the glaciers and the ice streams are responding to a whole host of different forcings. So this is one of the first examples that we were able to do with this kind of thing, take lots and lots of satellite observations, pile these things together, and start to look at how a particular ice stream, this one that we've been looking at, that's located over here in West Antarctica, known as Rutherford Ice Stream, how this particular ice stream is responding to forcing from the ocean tides. And so what you're seeing in this movie are observations that we took from lots and lots of satellite observations. And this is the change in the total flow speed within this ice stream, and this change in response to forcing from the ocean tides. And so the main component, the main frequency of change that's happening within the surface velocity field is taking place at a period of a fortnightly period of about 14.76 days. And this is the spring neap cycle of the tides, if you're familiar with this. It's all related to the alignment of the Earth, Moon, and the Sun. And so you get the spring tides, that is these maximum tides, whenever the Earth, Moon, and the Sun are all in alignment. You get the neap tides whenever the moon is about 90 degrees offset or so from the Earth and the Sun. And it's this period, it is this beat frequency that you get between the solar and the lunar tides that ends up driving changes in the horizontal velocity of the glaciers. And we're very interested in this kind of thing because it introduces this possibility of kind of exploring this in this classical dynamical systems sense of the problem. That is that we are able to observe the response of this complex system to forcing of a known frequency and a known source, that is from the ocean tides. And so we're able to use this kind of thing as a diagnostic tool and look at how this signal that originates over the floating ice shelf, which you can see down here kind of in the bottom right-hand side of the movie that's playing, how the signal that originates over the floating ice shelf is able to propagate upstream through the grounded ice. And we can use that propagation, the rate of propagation, the rate of attenuation of this propagation of the wave and so forth, in order to probe the mechanical properties and the coupling between the ice and the bed, which is the primary resistance of the ice to flow. And one of the primary things that sets the rate of sea level rise, the contribution of this particular area to sea level rise. And we can go on from there. We've developed sort of new methods using lots of data that we have available to us now. We can start to capture more complex signals. And so we're looking at now the response of outlet glaciers and ice streams and so forth to calving of massive icebergs. And so that's what we're showing here. So we have images here, the radar amplitude images that we see, and you can see these large icebergs that are breaking off of this area in West Antarctica. One of the areas that's losing a ton of mass is known as Pine Island Glacier. And you can see these large icebergs as they're starting to break off. And on the right-hand side in this color map, you can see the changes in velocity. You can see the acceleration of the glacier in response to these icebergs breaking off. So again, this is the sea level signal that you're kind of seeing right before your eyes. These icebergs are starting to break off. What we're actually witnessing in Pine Island is this sort of catastrophic failure of this shear margin that exists on the right-hand side of the image. As this piece starts to break up, this floating ice shelf starts to accelerate. These big pieces, these big icebergs are breaking off. The glacier is accelerating in response to that, contributing more and more to sea level rise and so forth. So we monitor the kind of thing closely. We use these kinds of observations, again, the movement of the signal, the propagation of the signal through the system to try to get an understanding of the viscosity of the ice, the coupling to the ice to the bed, and so on and so forth, so that we can calibrate our models, so that we can develop new models, and so that we can get a better idea of what sea level rise is going to be in the future, develop these models to do a better job of projecting what's going to happen to this system. So I can start to wrap things up. Oh, I can see that we're close to the end of time. So we'll wrap things up. So I just wanted to give you all a quick overview on kind of a progress in understanding and projecting sea level rise. All right, so the observations that we use and many others help us to develop and calibrate these models that we use to project sea level rise. And a lot of, hopefully you picked up on some of these bits that a lot of the observations that we use are the same tools that astronomers use and so forth. We just benefit from the fact that we live on Earth. And so our instruments are a little bit closer to our target than what astronomers have available to them. But as time goes on, more satellites fly, more aircraft fly, we get more observations. And this is basically gives us the ability to do a better job of reducing and, more importantly, quantifying the uncertainties in our projections of sea level rise so that we can plan accordingly for our future. New technologies that are being developed that hold the potential to really accelerate our understanding, accelerate improvements in our projections of sea level rise, our managements of risk of climate change, and the issues that people and society face and so forth. So I can just end it there, I think, since we're at the end of time, and maybe we can take a couple more questions.
Yeah, thank you very much. I really love this in-depth look at why there are some uncertainties about, how much is the sea level rise, is the sea level going to rise? So I really appreciate that. What I will do right now is to go back. We had some great questions come in over the past few minutes. I'm going to come back to those. If anybody else has other ones, feel free to put them in the chat. One question was from Sophia, thinking about the ice sheets on the seafloor. Would changes in temperature of the Earth's core also affect melting?
Oh, That's an interesting question. So it's definitely the case that geothermal heat flux, so the heat that is coming out of the solid Earth, is an important contributor to melting in ice shelves or ice sheets. And there is a really interesting feedback actually that takes place between ice sheet loss and the heat that comes out of the Earth, which is to say that at least over geological timescales, if we're thinking about glacial cycles, right? So the formation of and the collapse of ice sheets over timescales of kind of tens of thousands of years and so forth. Whenever you take an ice sheet and that you've had sitting on the solid Earth for a while, and you start to remove that ice sheet, you start to remove the weight from the solid Earth. The solid Earth starts to rebound, as people mentioned before, and of course, it also starts to changes the pressure, reduces the pressure deep within the Earth, and then allows for depressurization melting that takes place within the mantle. That can enhance volcanism. That can enhance the transport of magma toward the surface of the Earth, which can increase the heat flux that's coming out of the solid Earth, cause the ice sheet to melt even faster, and so forth. So there's a fascinating feedback loop that's reasonably well understood between the loss of an ice sheet and the increase in heat that's coming out of the Earth, which causes the ice sheet to then decline even faster, and so forth. And in addition to that, all this volcanism and this transport of magma and so forth also carries with it CO2. So the mantle is the largest reservoirs of carbon dioxide on Earth. And so there can be a significant flux of CO2 that comes out of the mantle, drives further warming of the climate and so forth. So amazing feedbacks between the ice sheet, the solid Earth, the heat that's coming out of the solid Earth, as well as the CO2 flux out of the solid Earth and influencing climate. So that's a great question, Sophia.
Is there any danger of that becoming a runaway process?
Not so far. So there should be, regulating mechanisms on this. I mean, this sort of thing has to be qualified by the fact that, at least according to the models that we and others have run, the amount of CO2 that you would expect to outgas from the mantle in this sort of process is still kind of, on order of what human beings create every year or so through emissions. So we're still the runaway process.
We are. Great. Great. Okay. We've got a question from James. Does Antarctica record any earthquakes?
Oh yeah, definitely. So not much in the way of tectonics really in Antarctica, but there are earthquakes that are created. Most of the ones that we know about, at least, are from the ice itself. And so there are certainly earthquakes and seismicity and so forth associated with the break off of icebergs and whatnot within Antarctica. So we don't have a whole bunch of data from seismic stations in Antarctica because it's not the most hospitable place in the world to put instruments like that. But the few instruments that we do have certainly record a non-trivial number of seismic sources, many of them associated with the fracturing of ice and whatnot. We'd love to have a lot more seismometers down there so that we can study this kind of thing. But yeah, definitely.
Okay. I'm gonna, since we're in the questions right now, maybe you can stop sharing your screen unless we need to see anything here.
No, totally. I just had to find my.
Okay.
I've lost my cursor. There we go.
There it is. Okay, excellent. Another question from James. Are there any other areas that are high risk of melting or collapsing that other countries may be studying in Antarctica?
Yeah, I mean, lots of people from, it's an international effort to understand what's happening in Antarctica. And there are a number of places that are changing over time. We simply focused primarily on the Amundsen Sea sector, this area of West Antarctica and so forth that's changing because that specific area is the largest source of uncertainty and kind of an interesting story to tell and so forth. But the fastest changing parts of Antarctica are really taking place on the peninsula itself. So this northern most extent of Antarctica where the Antarctic Peninsula is coming up, and it's starting, it comes close to South America, just separated by the Drake Passage there. So that's the warm part of Antarctica, where ice shelves are collapsing, where glaciers are starting to speed up and thin and recede and so forth. And so there's a considerable international effort there to understand what's happening in the peninsula, what is the fate of the ice shelves in particular within the peninsula, what sort of mechanisms can drive the collapse and the change of the ice shelves and the speed up of the glaciers and so forth. And then loads of work is being done over in East Antarctica as well that we just barely touched on in this particular talk. But there are a number of interesting outlet glaciers and ice shelf systems and so forth that exist in East Antarctica that people are spending quite a bit of time on. So yeah, massive international effort to understand what's going on in Antarctica.
It's an important topic, and I can understand why people want to know what's going on there. I had a question that went back to earlier in your talk when you were talking about the Grace spacecraft that are weighing the ice sheets. And just first of all, I just want to note this that it's the same technique used by the Grail spacecraft around the moon, and just looking at the crustal thickness of the moon. So that's pretty cool. And one of the things that you mentioned, the similar techniques, just looking up versus looking down or around different bodies. But how long have these been operating so that we know what has been happening with these ice sheets and any changes in them?
Yeah, definitely. So Grace launched in the early 2000s. I know that we have good data coming from Grace, at least starting around 2002. And then that data set is pretty well continuous. So there's been a new mission flown called Grace Follow-On. It's simply new versions of the same Grace satellites that are continuing to fly now. And so we have this nice continuity of data sets spanning at least the last 20 years or so.
Wow, that's great. Yeah. Okay, wonderful. We have one final question, and just wondering how often you have been to Antarctica.
Yeah, that's a funny question. So in spite of the fact that I study Antarctica pretty much continuously and have done so for for over 10 years now, and I got into this business so I could go to Antarctica, I have yet to make it to Antarctica myself. So I don't really go down there much. My group and I, the research that we do is we use a lot of satellite observations. We derive a lot of mathematical theory, things of this nature, things that we don't necessarily need to go to Antarctica to do. But I'll make it down there one of these days. Other folks go down there every year. So there are a number of people that go down there quite regularly to maintain instruments, to collect sort of regular and periodic data sets and so forth. And so, yeah, it varies from... Yeah, I know people who've gone down there every year for the past 20 some odd years, and they love it. And then there are people like me that spend their career studying these things and never go down there. So it runs the gamut.
All right. Well, I hope you get to go soon. Yeah, absolutely. Well, thank you so much. That was really fascinating. We really appreciate your spending your time with us.
Yeah. Thanks for having me. And thanks for all the great questions.
Yeah. So I wanted to end tonight just by thanking once again our sponsor, Peppercorn Games, which provides community game nights, interactive theater, and pop-up performances in Flagstaff. And I'd also like to thank the Arizona Office of Tourism's Visit Arizona Initiative Partnership Grant, which helped to fund this year's iHeart Pluto Festival, as well as our members and donors who make digital programming possible. Thank you, everybody, and good night.